My name is, so as you already have heard, we will make a recording. So if you don't want to make to be on a video later on, please let us know by email, so we will cut it out. Otherwise, please feel free to ask any questions during this tutorial, and um, we will also pause the video during the Q&A session at the end. Okay, good. So welcome everyone. My name is Yuri Lysagorsky, and Matusz Mrowitz will help today, together with Mariana Forts, will help me today with managing this meeting, our GRACE tutorial, where we will cover the latest development and present you the usage of our GRACE Maker tool. So I think before going to this, a little bit about the way how we will proceed. First of all, you already should receive the installation instruction following that. But if you did it install and you want to follow, please, you can follow the tutorial. If not, or if you have any issues while following, because I probably will be a little bit faster than usual, we will, so you can do it later on your own pace. So just be sure that all these tutorial materials are in this documentation page, so you can find it here, starting from installation instruction and so on. And yeah, I would like to maybe give maybe a short overview of what we did before and how we continue to work with GRACE, just to have some historical context. So first of all, it was a tool called Pacemaker and corresponding performance atomic cluster expansion to as an underlying mathematical model behind that. And it's already like several years on scientific market, so to say. And more information about that you can find on the Pacemaker docs.io and on the corresponding GitHub pages. So it was quite a big increase of a number of papers that using this pace. So for example, you can see it's like a lot of paper from this year and it's still running. So a few of them in the pipeline and archive. And it was quite a successful application, and we're really glad that people do use it. And as you can see in this case, so typically the elements or systems that was studied by PACE and Pacemaker quite vary, starting from elements, pure elements, alloys, covalent, insulator materials, organic materials, and so on and so on. And usually it goes up to 5 elements in some applications like here and here. So, but on the other hand side, so this is kind of practical application limitation of the PACE models due to the scaling of the bases. But on the other hand side, despite of that fact, you still can do quite good and nice science with that, especially large-scale simulation using GPU acceleration. Here are a few examples that we want to highlight. Some of them already published, some of them are still on the archives. But MLPace allow you to run simulations for almost million atoms, so 500,000 atoms, and for multiple nanoseconds, of course, using powerful accelerations. But today we will speak about the kind of extension of this model towards graph atomic cluster expansion that will not replace but complement ACE and PACE. So we will refer to that as GRACE models for short. And first, I would like to bring your attention towards this table or overview of a series of ACE models where you can see the both Pacemaker and GRACE-maker tools and corresponding type of models. And I would like to explain quickly before we go to the tutorial about the difference and how we can, or how you can use, in which situation you should use this model. So as I mentioned before, PACE with the Pacemaker for parameterization, usually suitable for up to 5, maybe 6, sometimes number of elements due to the scaling of the bases, which does support TensorFlow and C++ custom calculator for ASC interface, and for LAMMPS for CPU and C++, the same implementation. For GPU, it's Cocos-based acceleration. It's also allowed to do uncertainty indication based on so-called the optimality criteria, so-called Maxwell algorithm. And what we learned from application of our models, it is very good for specialized potentials when you have few elements up to 5. So GRACE series of models allow to extend applicability and, first of all, removes the limit of number of elements that allow to being used or parameterized with the model. And it's also extended in terms of accuracy, but of course by cost of some price or computational performance. So the difference between, so the first model in a row that we will cover today, Grace FS model, which is a just extension of PACE towards multiple number of elements, and it's closest one. So we kind of do use almost very similar C++ backend to being able to run these models, which also supports the same type of uncertainty indication like the optimality, for example, but it can be used for multiple elements. We will see today an example for high-entropy 25 element dataset parameterized with this Grace FS. If you're going further, it will be Grace 1 and 2 layer models, which we refer to mimic the kind of topology of the Grace basis functions, which resembles the message passing rounds in other models. So here we do call them graph basis functions, where we do have local basis function, which is star-like in terms of the graph, whereas for Grace two-layer model and stars and so-called trees. Maybe it sounds a little bit abstract. It's not super important now. You can just think of this as local and semi-local models, corresponding basis functions. So these two models, they do have only TensorFlow implementation, and they allow for the moment only ensemble-based uncertainty indication, but they can be more accurate but more expensive in terms of computational performance. Okay, so now we would follow the tutorial. So I would go now to the gracemakerreadsthedocs.io, the homepage of that, where you can see the same table and explanation. And before doing this, going to the tutorial, firstly, we very quick, this time, very quick kind of overview of what you can find here. So first of all, this is the installation instruction, starting from the setup of Mambo Conda environments and TensorFlow, TensorPotential installation. You can install it from pip now. If you do want to have CPU support, please, this Grace FS model, so please install this extra repository from GitHub, which you can compile with CMake. And for Grace, in LAMMPS, you can also use this particular repository. We're planning to merge it into main LAMMPS branch later. So, but currently you can use it from this current our repository. So in order to build it, LAMMPS with support of TensorFlow and Grace. Okay, so as a quick start, you can overview the typical steps that we usually do have when we do model parameterization, starting from data collection to input file setup, running the GraceMaker, export the model to format that can be used by one or another calculator, building active set for Grace FS models only in order to perform uncertainty indication, and then usage this model in ASC or LAMMPS. So I would not go too much deep in the details for this quick start because we will follow the same steps during our tutorial. Okay, so then maybe we can jump towards tutorials now and tutorial page. So the prerequisites to having to running these tutorials on your hardware is to having Linux or Mac OS. So for Mac OS, maybe you want to have custom TensorFlow, but out of the box default also should work, but no CUDA support on Mac OS as far as I know. For Windows Subsystem Linux, I've heard that it does support GPU, but I didn't check it. So if you still can run tutorial and also you use the model on Windows Subsystem for Linux on Windows, but with GPU, I'm not sure, so no guarantee. Maybe it would work. So GPU is highly recommended for running the parameterization, but multi-core also will be okay-ish, but significantly slower. And for software, as we mentioned, you have to install these packages from the previous installation page. So all the tutorial materials you can find on the GitHub, or you can clone this repository. You can find it on this web page here. And first, we will start from the tutorial number 1, which is parameterization of two-layer Grace model for aluminum lithium. So for that, I already have it. Let me do it here. I already have it kind of configured. So we go to the, so sorry for using Midnight Commander if you have some bad reaction on blue color, but I love it. So we can go to the folder number 1 for aluminum lithium, and let's go to 0 folder data, where we can imitate how we do usually get the data and from where. So let me put it here. So first we will unpack our DFT data, pretending that we get them computed from somewhere. And for that, I just do unpacking of the archive. So you can see here there are multiple separate subfolders with different prototypes like lithium BCC, aluminum FCC, and so on and so on. And it does contain the WASP run XML for our case, which is enough to extract the information from. So question about the building the proper dataset is kind of out of the main scope of today tutorials, but of course, we're happy to answer this question if you have in the Q&A session later on. So let's say that you have a following situation, that you have your DFT data computed and distributed in different folders, subfolders. So here we just need WASP run XML file. And now you can run the, if we would follow a tutorial further, now you can collect the data recursively from the subfolders by calling the Grace collect utility. So let me execute this. And this will scan through the subfolders and read the data and extract the energies, forces, and stresses. So it should be force consistent energies. So we do have interfaced only to WASP, but if you need to do it for other type of DFT codes, in principle, what does this utility do is to building the pandas data frame that contains following columns. You can check it in the quick start. So if you can make it on your own, or at least ask if you want to adapt other code, please feel free to ask. Also, while it's collecting, I would like to mention that sometimes you can have already DFT data in different formats, for example, extended XYZ format. And in that case, you will see it in the second tutorial, but I bring your attention now. There is another conversion utility, extended XYZ to data frame, which you can use out of the box just to convert your XYZ, extended XYZ data set to our format compatible with GraceMaker. Good. So here collection is finished. As you can see it found 2 elements, aluminum, lithium. No reference energy provided, so it's just 0. It contains 600 structures, 11,000 atoms in total. Energy range from -3 to +6 eV per atom, and force magnitude from 0 to +4 eV per angstrom, which is quite moderate range. So main outcome from that is a collected pkg zip file. You can see it here, and we will use this file in order to run the parameterization later on. So now, following the tutorial steps, we finish this unpack and collect the DFT data part, and let's go to the parameterization. So we will do it in a separate folder. It's always recommended to have a separate folder to run parameterization, and we will use utility called GraceMaker -t in order to build the template input file, which you can later on manually tune. More information about the input files, input YAML, you can find on this input file section. We try to keep it updated and self-explanatory as much as we can. Sometimes maybe it's missed some information. Sorry for that, and please let us know. We will fix it. So now we go to the new folder where we will run the feed. Good point. Where am I? Here. Let's do it on another machine. Yeah, here on this machine. So we will go to this folder 1 for the feed. It's already some leftovers from previous run, but we will just do pretending it's now there. So we will run the GraceMaker -t for generating the input file like that. And after that, we will see some list of questions that we have to answer. It's like an interactive dialogue. So it seems to be our network file system slow down again. If it will be so, I will do it on another. Okay. Yeah, so generating input YAML. First, we need to provide file name to the with the training data set. In our case, that was, so you can follow it in tutorial. So here, this is a file name, collected pickle.gzip. I will just copy to avoid any errors. Then you provide test dataset file name, so there is no test dataset. Then we can use just fraction 5% of the data for the test set. A list of elements can be determined automatically later on. And now the important point, we have to specify model preset available. So it's model of different complexity. You can see already this FS, Grace 1 layer or Grace 2 layer. In our case, we will use Grace 2 layer model. So just provided name, and you can specify roughly a model complexity by providing one of the three categories. So we will go with small model here because so just demonstration purpose. Cutoff in angstroms, so you need to provide it. So this cutoff will be 1 for every bond type, let's say 5 by default. But I would like to bring your attention that it's possible to provide a custom cutoff. You can find it in FAQ section. Can I have different cutoffs for different bond types? When you can provide the, this input YAML cutoff dictionary with the options. For example, you want hydrogen bond shorter or some elements bonds larger and so on, because this will direct influence on the performance, the number of neighbors in the local neighborhood, and direct influence on the performance. But let's go back to our tutorial. So we will provide default cutoff, which is 5. Loss function type by default, we will use Huber. And Huber, for Huber loss unit, so-called parameter delta, which characterize its switching from square to linear error contributions. And then we provide energy and force loss components. So for energy loss weight, by default, we take it to 1, but it could be any arbitrary number. You can check it later. Here, contrary to pacemaker, when you provide just single parameter called kappa, which just do the balance between energy and force, here you can have multiple loss contributions from, for example, energy, forces, stresses, or maybe other. Later on, we can incorporate other kind of observables. So then it's easy to just specify one scalar, which was maybe empirical, but one for each of the quantities. So for example, for forces, 5 is good enough in the unit that we deal with, which is EV per angstrom. And for stresses, in our case, we will also provide 0.1 because we do have stress data in the loss in the data set. And we have an option to switch loss function. So by changing the weights of energy, force, and stresses after a certain number of epochs. In our case, we will do it after 350. By default, it's not, but we'll do it after 350 iterations. And the learning rate after switch should be reduced, which will be also this default value. Energy weighting after switching, you can specify. So for example, usually energy have larger weights and forces will be lower relative weight. So we just specify default values here. And energy type weighting scheme, which is similar to a pacemaker, we will provide energy-based weighting scheme, which means that in the loss function, structures which are closer to the convex hull will have higher weights, higher contribution to the loss function, and the same for atoms with more forces by magnitude, they have less contributions. The closer to 0, the more contribution have, because it's focus attention of the model towards closer to equilibrium configurations and make it more accurate in this region. This is what you typically need. So this is identical to what we have in the pacemaker. So weighting will be this energy based, and by default it's computed with respect to the convex distance from the convex hull. So I will comment on that later. And the last option is a batch size, which is by default 32, but you can increase or decrease it, depends on available memory. And the second point, that for the optimizer that we're going to use, so-called Adam optimizer, batch size define how many portion of data will be passed through the optimizer, how many updates will be effectively done. So if it's a very small number, so these independent batches, they will be quite small and maybe noisy with respect to overall data set, underrepresented in a way, but you will have multiple updates. If it's too big numbers, then maybe you will get better approximation of the overall gradient of the loss function when you do the model parameterization, but you will get less updates. So there is some empirical rules, and usually it's something like few dozen of structures. So we do use 32, but you can play with that depending also, for example, memory requirements. If you have low memory GPU, so you can reduce it for very expensive model, and so on and so on. So as a result of that, you will get input YAML file. So it will produce input YAML file, and now we can run the Grace Maker. So we can just run it without any other options, but by default it should take them input YAML. So it's loading the library. So we are working on the network file system. That's why it's a little bit slower. Okay, but not that slow. Good. So now you can see the output produced by GraceMaker. But first of all, I will come to that. I would like to bring your attention to this input YAML file, because now you actually look at it and let me open like that. Look at it and modify by hand if you want to tune one of these parameters. So you can easily find the description of these fields in the documentation in the input file section here. So for example, you can see the file name. Optionally, you can, if you do have several file names, you can provide it through the brackets, so square brackets. Test set size that we provided, reference energy for the single atom energy of each species type that will be subtracted from the energy provided in the data set. Currently it's 0, so nothing to subtract. We just do fit to the original raw WASP energy in that case. And but if you do have any other reference energy, so we do use it mostly to get the smooth transition, the cohesive limit. Whenever you pull up atoms apart, we go to the cohesion or the cohesion limit. And in that case, radial functions will go to 0 because of the just smooth cutoff. And second, energy also should go to 0 at the large distance. But if your data is, if you didn't subtract single atom energies from your data, it's not a big problem in principle if you will deal with only compressed or condensed region of your configuration space, but it could be a problem, especially in these abrupt changes, when prediction must go to 0 because of the radial functions and your data is not 0 aligned. So it's recommended to use this reference energy. This is a must-have option in pacemaker. Now it's not so critical. It's also probably not very critical for the pacemaker nowadays, but it's recommended to have this data shift. Controllable data shift, physically inspired data shift, not from the data distribution, but really from the physical considerations. So we define this preset here, which we enter. So it could be one of these presets. It also could be some custom model, but we would not discuss it now. And this is a collection of model parameters as a keyword arguments. More about these parameters you can find in the documentation if you would follow the preset page here. Here we describe these parameters for this FS, Grace 1 layer and Grace 2 layer presets. So you can play with them if you want. So now it's okay. Now parameterization is running. You can see it's very, very fast, and now it's in the epoch iteration 73 out of 500. And what we missed, I think I can see it in the log file. So yes, while it's running, all the output files will be saved in some of the subfolders that you will find in the seed folder here. So we did run, I will demonstrate it now. In this input YAML, you have a seed number 1, which is define all the random seeds, which is related to data split, trend test set, initialization of the initial parameters, and so on and so on. So all related, all the runs with this seed, random seed, will be saved in this folder. So first of all, there is a log.txt file that let me find it from the beginning here. This is our start today at 16:23, where you can see, yeah, here it is. from somewhere here, where you can see all the same information printed on the screen. Also, it specifies, it shows the batch size, it specifies the loss function, reads the data, or it could be a collection of the training data as a list, like a list of strings of names of the speaker GZ files. We can combine them together here. Then it will be unit conversion, computing of some constants and so on. So also building the neighbor lists, applying the weights, all the standard stuff. You can read it through. And I want to bring your attention slightly to this line, which is a train buckets 10. And after, let's say, several steps, it will be, I will make it visible here, it will generate the statistics of the train set. So here you will see in this brackets plus something %, which shows the extra fake or padded data, like fake structures, fake atoms, and fake neighbors, in order to have reduced number of model recompilation. So the difference from maybe different frameworks that we do use TensorFlow with XLA backend for this acceleration. And it requires a fixed input shape of this computational graph. It means that if we will have batches, and in one batch we have, let's say, in both batches we have 5 structures because batch size is 5, let's say, but it has 100 and 110 atoms and 1,000 and 1,000 and 10 neighbors, so different numbers. It will be seen as a different input shape, and it will read to the recompilation of the model for the best possible performance. To avoid this too frequent recompilation, we do use so-called padding internally under the hood. And what you should kind of just keep your eyes on, not even necessary to think about too much about this, but it's about the amount of extra padded, let's say, neighbors, so atoms and so on, which you can check in this log file. And if it's too big, like if you will see 100% or so, you have to increase number of buckets, because one bucket characterizes a group of batches that will be padded to the same level. If you have multiple possible subgroups, they will have extra, so small amount of this extra padded numbers. So just increase number of buckets if you have too high neighbors here. I think in the future we'll make it even automatically, so you should not think about this at all. So model is running. So now parameterization is running. So you can see that it's has the first iteration. The first iteration is the slowest one because it will do the 10 recompilation, JIT recompilation for each of the stain buckets, and the same it will do the extra 5 recompilation of the graph for test set. But after that, it will be very fast. So as you can see, it's just flying because it's, first of all, small data set, and it's A100, so it's quite fast. In the meantime, I can demonstrate what you will typically see here in this output. So for each iteration, that will be loss for, so train and for test, it's always will be in a bracket. So a loss function for train and for test. Mean absolute error for delta energy per atom for train and for test, it's in EV units. The same for RMSE for delta energy per atom, mean absolute error for force components, root mean square for force components. And since we also do run the use stresses, it will work for, it will show also Maya and RMSE for stresses. And also the timing in microsecond per atom. So it's like 19 microsecond per atom for the test evaluation, which doesn't require the computation of gradient of parameters. So this is a timing of the model. It could be even faster, maybe 2 times, just because it's small batch size and it's not yet saturated. So sometimes you can see this reducing learning rate messages. It happens because in input YAML, by default, we have this option for learning rate reduction, which this is a quite classical for neural network parameterization. It has so-called patience parameter. It means following. On every epoch, we do estimate the total, so test loss. And looking at this number, if this number goes down, it's okay. If it's not goes down but goes up or did not improve, If it didn't improve for the last 5 epochs or iterations, then we will reduce learning rate by this factor, which make fitting a little bit, let's say, more accurate but slower, but you're already in the right region of parameter space. So this will happen after every 5 unsuccessful epochs when there is no reduction of the test loss. So if learning rate will reach this limit, then it will stop and switch to the next stage. In our case, we do have energy force stresses as the first stage 1 to 5 to 0.1 as we introduced in the interface in this Gracemaker -t, but after 350 iterations, it will be reducing down to 10 to -3, and it's continue with new weights. So in principle, it happens automatically under the hood, but you may want to play with that if you really want to extract more accuracy or train your model even more. So also here you do see the compute convex hull parameter equal to true, because we request to have weighting with respect to a convex hull. It's again, all happens automatically. I just have to warn you that if you want to fit multi-element, multi-species, multi-elemental data, multinary, then just from computational science, you can check that computing the convex hull for the high dimensional dataset is scales very badly. So practically up to 6 or 7 elements, and after that, it's just computationally very unfeasible task. So it means that it would not work. This type of energy kind of accent would not work for very diverse data set when you have a lot of elements. But there are other options. You can check it in the input YAML documentation for dealing with that. So the batch size we provided here, and this is the number of buckets, 10 and 5, that I was describing beforehand. So automatically, when Gracemaker is running, it will save in parallel 2 type of checkpoints. Checkpoints is the current version of parameter that is learned up to now. First of all, it will be always best test loss checkpoint, which depends on how do you improve the test loss. And second is a regular one, just every something steps, for example, every 2 steps, it will save the checkpoint file. And if you want to have, for example, due to some reason, the complete history of the checkpoints, you can uncomment this line to save all regular checkpoints to true. In that case, of course, it will be much larger in disk size requirements, but you will see you can always go back in history and start refitting from this time step or export this model. Okay, it's finished. So while it's finished, you can see it's always takes the last best test loss model, the checkpoint from that, and export this model automatically to the final model folder. I will show it in a moment. So as I mentioned, so you have all the outputs of the current run and the corresponding seed, current random seed, and the corresponding folder. So here you do have checkpoints. You do have checkpoint for the, let's say, regular one. You have these 2 files at a checkpoint for the best test loss, and you have checkpoint from the stage 1 of parameterization if you want to go back to this moment of your fit. And you have final model checkpoint here, which is generated right now, which contains, actually, this is a saved model. This several files and folders. That's how we store the data when you want to run it or use it further. So let's go back to the tutorial, and I will just point where we are now. So we run this, Gracemaker, it's finished, or you can interrupt it in the middle, killing it with your favorite way in Linux. For example, Ctrl-Z or some other, kill -9. So I want to mention that, for example, if you want to have ensemble of the model for uncertainty quantification or at least indication, you can use out-of-the-box ensembling of the model. So mean training the same type of model, but on different subsplit of the data with different random initialization of initial parameters. And you can easily do it by just providing the seed as an argument to a Gracemaker. So you can just run this Gracemaker seed 2 and Gracemaker seed 3 to have 2 extra models, and they will be saved just in independent subfolders here. So it should be as easy as that. Now we can even analyze visually the learning curves. For that, there is a Jupyter notebook. You should be able to find it You can either look at it in GitHub, because it will be here, or I will open it on my Jupyter. Let me make it larger. Fit, visualize metrics. So I would not rerun it now, because I ran this example several times, so it will be a little bit messy. But typically, so what you can check, so first of all, you have to import it from the potentials utils, import everything. Independently from that, you can visualize the data set. So our data set is stored to the seed, random seed 1, and training set pickle.gzip and test set pickle.gzip. You can load this and, for example, visualize the actual distribution of energy corrected, and so on and so on. So this is our energy and distribution for train and test, from -4 up to +6. It's logarithm scale, as you can see here. Force component distribution, so it's more or less uniform data. Stress component distribution also, well, maybe slightly non-uniform. And you can automatically visualize the learning curve from that. What you need to do, just follow this example, create empty dictionary, automatically discover fit folder starting from this root. So I'm in a current fitting folder, but you can have several experiments, so just initialize it from the 2-level above. So if you run multiple fits in different folders, just to compare and select the best model, then it will automatically discover the log file and the information about the train and test metrics saved in the separate files. It will be in these subfolders. It will automatically read them, and you can now, for example, in that case, because we did compute energy-based weighting scheme, we have a subgroup of structure that is close to convex hull. It has special name low. Then you can address to that like that. Otherwise, you can find as examples of this visualization in the examples of documentation to the GraceMaker. And long story short, here our learning curves with respect to number of epochs for my force component and for my delta energy per atom. You can see these 3 different splits. They converge to more or less the same 6 or 7 millieV per angstrom for force component. And for delta energy per atom, it's 3, 6, and that was unlucky split probably, or maybe I interrupted early, so I don't remember, but okay, maybe one outlier. But more or less it's more, let's say, uniform fitting. So this is optional. You can also get used to control this by looking on the table, on the log.txt without visualizing, but if you want, you're welcome to use this. Now let's go further. So we are on this step. Now we go to the step for save and exporting the model. For doing this, we will use following command. So it will be GraceMaker -R to read the best test loss checkpoint, and -S, sorry, to save it immediately. You can check more information about this this format here, but it will provide to us, let's say I'm pretending to run this GraceMaker -R -S. If I would run this, should I? Maybe yes. Let's try it. I hope I will not break the consequence step. It seems to be normal termination. So it will load the model, load the checkpoint, and export this to the saved model format. As a result of that, again, it takes a little bit of time because of the network file system and TensorFlow library that loaded under the hood. That's always with Python on network file systems. Yep, but here it is. So it's just load the model configuration. It's loads the best test checkpoint because that's the default behavior. So it's read it from here and export it to the saved model folder in there. So you can see this saved model. This is exactly what we just exported. Okay, that's how you can kind of prepare your model to be used by either ASC and Python or LAMMPS. So now we go to the next step, usage of the model with Python ASC first would be. So you can check this notebook. I will open it on my Jupyter. You can, if you want just to visually see it, you can also open it directly on GitHub because it should render this Python notebooks easily. So what we do have here, most important thing, you have to import this TP calculator from tensor potential.calculator, and now you can load this calculator by providing the path towards this saved model. If you have normal termination like final model, then it will be passed to the final model. If you terminate it somewhere in between due to the wall time on the computational node or other reasons or some crash, you can always export from the last checkpoint and continue using as a saved model. You can rename this as much as you want, just don't touch what is inside this folder, but you can rename it as much as you want. It's just the name of the path, which will be used by TensorFlow to load the model. So here we create aluminum bulk. Let me check, may I re-execute it? I always check if I get the same. So you can see it's a little bit slowing down now because it's the first run. And actually, this is slightly different numbers. Okay, anyway, because it does compile the first time as the graph under the hood with JIT, just-in-time compilation using XLA, given the current structure size, like number of atoms or number of neighbors and so on and so on. I think number is slightly different because I didn't run up to the end on the last tutorial, and that was leftovers from the previous tutorial. I'm not sure, so it's not a problem. What I want to bring your attention here is to the this extra arguments, that is path neighbors fraction and path atoms number, which has non-zero default value, which exactly characterize how much extra fake neighbors, let's say 5% here, and fake atoms, like one fake atom, will be always added. And if you will, or if this calculator will face a new structure with more neighbors, for example, because you compress it, then there is still place to use this fake ballast atoms in order to avoid extra recompilation. This is so-called amortization way of amortization approach, how you can avoid this extra recompilation. But in principle, it should not affect anyhow to your overall performance because compilation happened once and then it's super fast and you can use the model. So here we will run the for example, relaxation of this, and you see it's stable and relaxed. The same for lithium. And you see it was no any recompilation here because this lithium and this aluminum structure, they have both the same one atom only. This is a primitive cell. And it does use the padded number of neighbors from aluminum, I believe. And we can compute the phonons. Let's see if it would work. Now for phonons, it must to deal with the supercell 7 by 7 by 7. So of course it's recompile. It's take a little bit of time. But at the end of the day, it does it only once and then it's use recompiled version. Again, increasing the padded upper boundary, so it will not take any other recompilation further. So it's like cumulative maximum. So the more you use the model, the less frequently it will be recompiled. And you can see, yes, there is a quite nice band structure, a phonon band structure and phonon dose for our very quite simplified potential that we just fitted in front of you. The same for lithium, I think I would not run it. What I want to run is another example. So yes, and I have to mention that you can see the nice and beautiful phonons because forces and energies are consistent to each other. It's just direct derivative according to definition. And it's rotational invariant. So it's not what you always can achieve using other type of the models, which does not respect rotational invariance, I would say. We will see what it will bring us when we'll go to the foundational models. So the same for lithium, but I would like to demonstrate you also ensemble calculator. So if you want to have a, let's say, kind of feeling about the uncertainty indication of your model, you can provide as a first argument, which is called model, just a list of paths. For example, we have prepared several runs of the saved model, and then prediction of this calculator will be averaged out, and as uncertainty, we will use the standard deviation of this prediction. So energy and forces will be averaged over the 3 prediction of each model. So it will be, of course, 3 times slower, but you should not use it always. Okay, so in that case, I will create this calculator. And here I will run a screen through the lattice constant of aluminum from 1 to 8, create this in place, and compute potential energy with this ensemble average prediction, and then take energy standard deviation as a measurement of uncertainty. It takes some time, but once it compiled first time for the most dense structure, it should run quite fast, I believe. Anyway, I have already result of that on the next. Okay, here it is. I can rerun it. Yep. So here I do select this threshold for standard deviation of energy as 10 millieV, just because that was more or less average mean absolute error during the fit. And given this threshold, you can see that this part of energy lattice constant curve mark as interpolation, because in that case standard deviation of ensemble below that, otherwise it's above. And it's marked as a red. So you can have a kind of feedback from the ensemble of model. Well, this is very primitive and naive, but it's better than nothing. In order to get the feeling about when your model can behave or misbehave, or when it's not sure about its own prediction. Okay, so far so good. So now we finish this part with usage with ACE, and now we can move towards usage with LAMMPS, with the grace. So first of all, of course, you have to have LAMMPS compiled, but I have it and I will run it now. For that, I will go to the third folder, LAMMPS, and here we do have this input file. And so the main point that you have to use pair style grace with the path. So path verbose is optional. Option just provides, will print us detailed information about the padding during the simulation. So it's exactly the same padding that we have in the bucketing when we build together the training set, or when we did this, which happens automatically, this padding with extra fake atoms and neighbors. This is a mechanism how we kind of make the model compilation less frequent and make it overall more effective. So for the moment, I will use just what does this script is doing is it creates FCC with 2 by 2 by 2 supercell size. It's just pure aluminum. So here I create pair style grace. I ask for the path verbose, but if you don't want to have it, for example, it breaks some of your post-processing scripts or whatever, because it's non-standard LAMMPS output, you can remove this option. And pass to my model, the saved model or final model, or any model that contains TensorFlow saved model. And of course, mapping of the elements as usual. And after that, it will be initiate velocities, then it will be NPT, so 20 steps for pre-equilibration, then another 20 steps just for run. On this 20 steps, we will see several paddings, because it will gain a maximum number of neighbors, but on the second 20 we will not see it, so it will be good. I will execute LAMMPS. I have it built here. Let's hope it should work. And in parallel, I will also show you the usage of GPU. So I'm on the first. Am I? Okay, so it's already finished. It was fast enough. So I'll demonstrate it later. So this is output of LAMMPS. It loads the model. So it's first write the TensorFlow version, say that neighbor padding is on. It always must be on, otherwise it will be super inefficient. Padding fraction, it's here by default, it will add 1% of extra neighbors. And it also can reduce the padding. For example, if you have a decreasing number of neighbors, why to compute extra fake neighbors, you can decrease this padding threshold, and it will be more or less kind of in a smart way select one of the previously compiled models. So there is some smart things behind, so you can believe me. So it loads the model from the saved model folder, and now it's map LAMMPS atom type 1, which is aluminum, to a species type 0 from the model. And you can see the first time atoms padded here. It includes 3% of fake atoms, because it just only 32 atoms, so it's one extra atom at least, so it's 3% of that. The same for number of neighbors, so it's this total number of neighbors, including 1% of fake neighbor. And you can see it's run some dynamic, but in between it's did a reduction of number of neighbors just to have some efficiency. It was recomputing it once, and when we run it second part, another 20 epochs, just to have a clean timing, it will be quite fast. What I want to demonstrate you is the following. So now I will change the supercell size from 2 by 2 by 2 to 30 by 30 by 30 and run it once again and show you this usage of our first A100 GPU. You can see it here. So this is a memory usage, and it's also should be utilization. So you can see when there is some model compilation utilization 0, but once it's in place, then it's maximum utilization. This is 80 gigabyte of memory, so it's quite big. And now it's already running the calculation, so you see its efficiency quite high. And in 2 more, maybe 10 more seconds, you will see when it's go to the, okay, now again have a reduction because of changing of geometry during this run. So let's try to run it faster. And yeah, now it's a second part, another 20 steps. Now it will happen without any extra recompilation of the model, so it will be pure execution time that we can measure. And I would like to demonstrate it. So 20, 30, and 10 more steps. You see it's complete usage of the, almost full usage of the memory and complete utilization of GPU. So it's really on the cutting edge. So we have 24 seconds for one process for 20 steps for 100,000 atoms. So if we convert it into timings like divided by 20 steps divided by number of atoms, it gives us 11 microsecond per atom. This is the performance of this particular model. Well, it was small model, but still it was a 2-layer model, so it's quite expensive, could be quite expensive. And in average, we had just 81 neighbor per atom, so it's not so small, but it depends on the material density, of course. But you can reach something like this, like 11 microsecond per atom in this particular tutorial. So let me know, are there any questions in the chat, because I can't see the chat now. Can
Anton
I?
has answered them, most of them.
Okay, good. Because I don't see it at all. Anyway, okay, so far so good. We now did first part of our tutorial. So maybe we should have a 5-minute break now until 5, and then we continue with the second part. In the meantime, you can think about your questions, and we can pause the video recording. Okay, great. So let's continue now with the second tutorial, which will be dedicated to fitting the Grace FS model for high-entropy alloy with 25 elements dataset. And that we will export for following CPU support. So dataset for this tutorial was taken from this paper, which is extension of their previous paper. They did a really great job on putting together this data. It's really a nice dataset for having surface and bulk properties of high-entropy alloy with 25 elements covered. So optionally, you can get and use the whole dataset, but you need to download it and convert. So for example, unzip, and then you will have multiple XYZ files, so you can use our utility to convert it to the multiple pickle.gzip files. If you want to use it. In this tutorial, we'll use just one part of this dataset, which is bulk random train structures. That is the exact name from this archive. And let's assume that we already have it prepared before. So as we did, let me check it. Maybe I'm here. Yeah. So go to the second folder, high-entropy 25 Grace FS, and here our data, it's in pickle.gzip format. So we will go now to the folder 1 with the fit. And once again, we're going to use gracemaker -c in order to set up input file. So I will use it like that, gracemaker minus T. And we, as always, have to provide the path to the training set file name. So I do use this a relative path. Here, test dataset file name no, fraction by default 5%, list of elements, all elements found in the dataset. Now the model type would be FS, for Grace FS, and we again will use its small preset just to speed it up. Now the default cutoff would be suggested is 7. Before for two layers that was 5, because for two-layer models you effectively have larger perception range and like number of these interactions times cutoff. So that was effectively 10. Here it will be 7, which is default, and the loss function will use Huber once again. Huber loss parameter delta 0.01, energy loss weight 1, force is the same default 5. Should we use stresses? Yes, we're going to use stresses. So here in the bold marked non-default value, so you can just click them. We will not do any switching of energy for stresses weights in that case. Then we also use by default uniform weighting scheme, simply because you cannot came up with the convex hull for 25 elements such easily. It will be computationally very complex tasks, which we will not solve on the fly with the gracemaker, of course, and batch size 32. So you get once again input file, which you can tune later by hand, following all the previous recommendations, maybe tuning some of this parameters here, maybe changing the weights and loss function, and so on and so on. And so here compute convex hull by default is now false because we didn't request for energy-based weighting scheme because would not be possible here and now. After that, let me jump, sorry. After that, we can run the model parameterization with gracemaker or gracemaker input YAML. This is the default expected file name. Once again, now I will run it on another machine with RTX 3060. So you can see, maybe can I maybe demonstrate it now? So you can see this is 3060 RTX, and it will use, so currently it's building the neighbor list under the hood. It has a progress bar. After that, again, this number of buckets that we discussed before. Here you also can see that it contains 25 elements enumerated from 0 to 24. That's the elements mapping. Data set, training set is 9,500, test set 500 structures. Now we built this data set computed on the fly neighbor list. It has only 1% extra, which is good because it's quite big number, and data set is quite uniform. If you have not super uniform, different number of atoms and structures data set, then maybe you want to increase this train bucket parameter to have less overheads. And now it's actually, okay, here you can see some leftovers which I didn't switch off on this machine. This is from TensorFlow, and it's totally fine because now it's saying that it will do some JIT compilation. Sometimes it complains that maybe it's not the some details of this compilation, but it's totally normal operational mode, so don't be afraid about that. And once it will do it for now, it's on the epoch number 5. So sorry, it's on the batch number 5, batch number 8, because between that it did use already precompiled. It will do this compilation maximum 10 times, and then it will run quite fast, even on my RTX 3060 GPU on this particular machine. Well, I think one more, and we will be good to go. Okay, now you see it's much faster because it's, okay, maybe one extra compilation. Yes, now it's quite fast. Only the first epoch or first iteration is slow because of this compilations, but then this compilation will be reused because it's sitting in memory. Well, on RTX 3060, maybe you should run it for, I don't know, half an hour or so, I would say, or maybe a little bit more. But after that, it will have the final model already. Maybe a little bit more, so I don't remember exactly. But again, it's doable on normal GPUs, not only on A100 and so on. Sometimes you just have to reduce batch size if you want to squeeze it in. I think I will stop. So now it will do the same calculation for the test set, the same recompilation, but it's only maximum 5 buckets, so it will do it less number of times. You can usually switch off this extra visual noise by, if you go to FAQ section, you can reduce TensorFlow verbosity level by providing this environment variable, setting it to 3, let's say. And the same as we have seen before. So metrics after first epoch, and then it finds a new best test loss, save it as a best test loss checkpoint, and continue with the next iteration. Then you have to do it further. Okay, good. So I think I will stop it now, if I may. No. So usually I do it with killing like that because it sometimes prevents some background process with TensorFlow that requires more hard killing. Good. So let's pretend we waited for maybe 1 hour or 30 minutes. So we have finished this calculation. Then we can run once again Grace make. So let's go back to tutorial number 2. After that, if you want, for example, to manually continue the fit with a new parameter, sometimes it makes sense. Like, let me try to change the loss weights here and there. So what you need to do, it's better to copy the checkpoints and input YAML into new folder. So for example, in that case, I have this folder 1 fit. I will create a new folder 1b continue fit, and there I have to copy input YAML file. And you have to copy maybe the complete folder here that contains most important checkpoints, model YAML, and that's it. Basically, that's it. And you copy it correspondingly here, and then you can manually change, some parameters here. For example, I change the energy and force weighting manually and continue the fit. You have to pay attention that what is your initial learning rate is better to reduce it now because maybe you otherwise optimizer will be kicked out too far from the current parameter region when you just abruptly change loss function landscape. And you maybe want to switch off resume learning rate to false if you really change this learning rate here, because by default, a typical behavior, you just want to continue the fit. In that case, you want to just add extra iterations and you want to continue with the same learning rate as was in the previous run. So by default, this is here switched to true, but maybe it's better to switch it to false and start from the manually provided 0.01. Okay, it's all defined here. It's all defined here, so you can read it further and follow the documentation as well. So now we will go to the save and export of the model. So probably I would not rerun it once because I didn't run fit until then, so it's already broken. I will reuse the previously saved model after the normal run. In your case, if you just clone repository from GitHub, it should contain the good fitted potential, so you can execute this command. So I will, in order to export a model compared to what we had just for a Grace when we have -r-s flag for start from the best test checkpoint and save model immediately. Here we do add extra flag -sf also to export into the GraceFS YAML format, which will be used by C++ implementation. After doing this, let's pretend that being here, I run this -r-f-sf. I execute this command. As a result of that, in this working folder, I will get this fsmodel.yml file that will contain exported. You can check it. It's a text YAML file. You can check the list of elements, other parameters like embeddings and so on and so on. For example, this is a list of B-basis functions for species number 0 that was silver, I think. So it has running n index, l index, ms combination, cg, and so on. Maybe a lot of technical details, but if you're curious enough, you can study the functions here. What we're going to do now, and I think it would work, we can generate an active set for the given data set. So given the data set and giving the fitted potential, we can generate this active set using pace active set utility that came from pacemaker toolbox. It's exactly the same utility, but you have to, again, whenever you install GraceFS support, it should be installed from this branch. It's not yet in the main branch, but the good point is that if you install it from this branch, it will support pacemaker as well. You can have one all-in-one installation, GraceMaker and pacemaker, because it is compatible. Just this branch contains this extension towards GraceMaker, GraceFS models. So I think I will run this command here. Hope it would work. So I'm in this place where I do have the model, exported model by itself, and also the training set that we defined, which is automatically saved here by GraceMaker. So I should run this model here. I hope it will work. I don't know. Yes, 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 it is because of the right environment. So what does it do? It's reads this train set. From here, it's found this 9,500 structures. Total number of structures is also one, because you can provide several files. If you fit to the multiple files as a training set, you can also provide several of them. It's get this FS model YAML file, you load it as a GraceFS basis set, so it knows what it's doing. And now it's identifying in the data set following amount of atoms of scandium, following amount of atoms of vanadium, and so on and so on. It has only 180 B basis function. That was small preset of the model. Now it will compute these B basis functions. So again, you can see it will take roughly 2 minutes or so. And after that, it will run Maxwell algorithm in order to, using this Maxwell algorithm to select, based on the optimality criteria, select the active set, most representative one. I think we can wait maybe 1 minute while it will be finished, because Maxwell here will be very fast. It's quite good in uniform data set. Yeah, so when we will have it done, we will switch to the next step of usage of the model. So we can wait. In the meantime, any other questions or comments in the chat? No, not yet. Okay, let's pretend it's running, but I already have the file prepared beforehand, so I can go further. So now we move to the next step, usage of the model. And you can find these notebooks in the subfolder. Okay, maybe it's one subfolder deeper now, so it's not very updated version. So we go to the tutorial number 2, Python ACE, and this is our Jupyter notebook. I think it's already loaded. Yes, I will just rerun it. So now we once again have two options. Option number 1, if we want to use this fitted model, we can use it through the TP calculator using GPU with all advantages and disadvantages. Of course, so we import here, we once again load the saved model or final model or whatever it is. I hope I have the right model. Yes, now we can create a structure, which is FCC gold, assign it, get the number. So first time it does compile. And I hope, yeah, it's spent some time for compilation. Now I get the number. And now I will, okay, you can get the stresses, you can get the forces, you can get everything. So no problem with that. Not all models nowadays can do this, unfortunately. You can run the fits, it's uniform, no problem with that, so it's converged. The same for surfaces. So for example, you can relax the surface, but I have to mention that this potential was fit only to the bulk data. It's never seen the surfaces actually. And it's likely didn't crash in that case, but it's mostly due to the good data set, and it's still covers here. So usually you shouldn't expect that it's not by default that you should expect that it will work for surfaces if you didn't fit the surface originally. But luckily it works, and probably you did notice that it was some slowdown due to recompilation at the beginning when this BFGS went to the wrong direction. It's increasing energy because probably try to compress it too much the structure, which leads to many neighbors, and it recompiles the model. But once it did it 1 or 2 times, it's now use the compiled model, and then it's run quite fast. So you can control amount of this extra padded number of neighbors. Let's say you can put it to 20% or 0.2, then you have less frequent recompilation in average. But again, kind of cumulative or amortized timing means that you recompile model once or 2 times, and then you use it many times, and then it will be very fast. Now we can do the same, but using our custom C++ implementation. For that, you need PyGraceFS calculator from PyAce package that you did install here in this section, GraceFS. I still hope it will. Yes, so let me copy this. It's the same number. Okay, very good. We can copy and compare numbers that we get. May I rerun it once again? 130, yeah. So we can have the same structure computed that was by GPU and TensorFlow that was computed, by CPU and C++. So you see it's almost the same numbers up to the last digit, which is just numerical inaccuracy of on different actually hardware here, so different order of summation and so on. Stress is also very similar, and it's also relaxed to the same ground state. So they are compatible, they are one-to-one corresponding. The same you can do with the surface now. So there is no recompilation, but it's only one core, so it's uniform, but slower because it's run on one core. But now the new point here, main point, that you can now compute extrapolation grade gamma by setting the active set to the our calculator, calcfs. Exactly this file that we get it here now. So once we have finished this base active set running, so it's construct in 2 minutes 39 seconds. It compute V projections. That's amount of the so-called design matrix. Then it's throw away outliers in the predictions by forces to avoid them, to have more reliable extrapolation rate. And then it's for each species, it just identifies a square 100. So 180 by 180 matrix for each of 25 element, and saved everything to this FS model ASI file, which is 6.2 megabyte. So here we do load this ASI file. So we can once again attach the calculator, get potential energy, but now on this calculator, so this structure.calc.results, you will have extra value, which is gamma, exactly this extrapolation gamma, which is per atom quantity. And in that case, it's less than 1, so it's as it should be because it's bulk FCC, it's an extrapolation regime, which is expected. Now I will do the same test. I will just have a loop over the different lattice constant, create this aluminum FCC, and get the maximum of extrapolation gamma, maximum over all atoms, but it's only one atom, and it will be the same number. And then we can visualize it like that. So here I just highlighted regions of this energy lattice constant curve, where we have this extrapolation gamma less than 1 or more than 1, because 1 is the threshold, very well mathematically defined threshold for the extrapolation according to the optimality criteria. You can see that in this region close to the equilibrium constant. So as far as I remember, 405 is the lattice constant for aluminum. Should be somewhere here, which is nearby. We do have interpolation, but if you go to the shorter distance or to the larger distance, it starts to extrapolate. So now you once again have the indication that in these geometrical configurations, your potential not sure about its own prediction. You can do the same for FCC 111 surface. I just now will plot z coordinate versus gamma. And you can see that for the top and bottom layers, outermost layers of the surface, extrapolation is more than 1, because once again, in our particular case, we did fit only to the bulk only data, so never seen the surface before. So it's which is it's indicate about. Good, which is expected behavior. Sometimes, so it's not 100%, let's say, like that. Sometimes you can see some fluctuations. Maybe it will be slightly larger, slightly lower, close to or larger than 1, closer to 1. Maybe this number will be closer, but generally speaking, in average, this is geometrical criteria that characterize when your model is close to the so-called outside of the training set convex in this B basis function space. If you want to learn more about that, I would refer you to this active learning strategies in atomic cluster expansion paper that we wrote for PACE, but the same mathematics is applied here for Grace FS because it's mild nonlinear model. For, as we already have seen, for the general Grace 1 or 2 layer calculator, the way to go is ensembling for the moment. Maybe in the future we will come up with a better way how to characterize uncertainties, but we believe it's important to have at least one of this mechanism if you want to be sure in your simulation. So here we have seen similar picture, but now it's with, let's say, well, first of all, it's different data set. That was aluminum lithium, and this is just different models and mechanism, but it works in the same expected way. Okay, so now let's go back to the tutorial. That was usage of the model in Python OAC environment and in LAMMPS. Of course, we need LAMMPS to be compiled with GraceFS support. So it should be done also automatically if you follow installation instruction. And let me run it here, maybe. I will go to another folder, 3 LAMMPS, and here we do have the following simulation setup. We have a gold FCC 111 surface structure. I think it's 111. And we will use, so let's check this in LAMMPS. Most important point here is your definition of pair style. Now it should be Grace/FS with extrapolation option, because you can not provide this option, then you do not need to provide active set, but then you will not have extrapolation greatest will be 0, cannot compute. So you have to provide GraceFS with extrapolation options, then you provide path to model YAML, model ASI file, active set inverted, element mapping as usual, and extra things that you now, this is already LAMMPS technicalities, but they're important. You will request GraceFS pair style, this GraceFS pair style, for getting so-called gamma. GraceFS know what does gamma mean. Request it every 50 steps. And then it will be per atom F GraceFS quantity in LAMMPS, that's the name of that. And then we will compute reduce maximum among all atoms to get the max Grace gamma, so maximum extrapolation rate among all atoms in the current simulation cell. Then we can also have yet another, this is already more technicality of LAMMPS. If you don't know how to use it, you can just do not pay too much attention to that, but if you're really interested in how to use it in LAMMPS, so you can now have yet another dump that will save to the disk current configurations, to the file called extrapolative structures.dump. Every 50 steps, this is synchronized with that, and we will skip this space dump, we will skip it if max space gamma less than 1.5. It means that we will save to the file only those structure which contains which have at least one atom with gamma more than 1.5. Otherwise, we will skip this dump and it would not be saved to the file. And yeah, I think this is just for stopping simulation if you have really huge extrapolation rate, but I think in that case it will crash even without stopping. And then we have just typical LAMMPS, so you can follow any tutorials anyway. We just add to our thermostyle, we can add the Cmax space grace gamma to Cmaximum extrapolation. And to regular dump, we can add this F grace gamma once again. So let me run it. P. First, I will run it on one. Yeah, I have to load model load PI sync Intel because that's how it was compiled. Now I will try to run it. Finger crossed. Here we go. Yes, good. Nice. So now we do run it on one MPI process, so one core actually. It's only 40 atoms in the structure just for demonstration purpose. So we do load this potential. It does support these elements. This is the number of functions, 180, and that's the mapping that we selected. Just we do use gloat out of these multiple elements. It's also loaded ASI file because we want to compute extrapolation. That was minimization. This is a dynamic, and in this dynamic, okay, maybe I can make it looking better in here. Yep. So this is a main run table. So you can see the Cmax space grace gamma, and in the simulation, I intentionally increase the temperature from 500 up to 5,000 just to break something, break the system. And you can see extrapolation rate. First of all, it's extrapolative more than one because it's open surface. Second, because it's increasing temperature. Sometimes it has 1.6, 1.7, 1.8, and it's saved into the extrapolative structures dump file. So now I can take what's the last step, what we can do. Now, after you run this, you can want to select some of the structures that has high extrapolative grade and most representative to take them, go to do DFT, add to your training set and improve the potential. So you can select, this is optional step, but you still can do it. You can select most representative structures for DFT by using paste select command. You have to provide paste select, you have to provide this dump file name, minus P pass to the potential, minus A pass to the atomic, so to active set inverted, and for LAMMPS you need a mapping of elements. If you do this, it will load this. Yep. So what happened? It loads this extrapolative structures dump from our trajectory. It contains 28 structures, then it loads potential and active set, and then after doing some matrix operations and yet another Maxwell algorithm, it selects 5 most representative structure out of this 28. So you can reduce your number of DFT calculation by using this paste select utility for GraceFM. Okay, now you can take, now it's stored in the selected PKG zip, which is a PKG zip pandas data frame. You can easily load it as we have before in Python and do whatever you want in order to do the DFT calculation with this. Okay, now we switch to the last part of our tutorial is using universal machine learning interatomic potentials. So as we mentioned before, using these Grace models where we do use so-called chemical embedding, there is no limitation to the number of elements that model can deal with. Of course, you need more data, maybe increase the basis set to have the proper to get the proper accuracy, but there is no bad scaling as we had in MLPace. So originally MLPace, I will bring you once again to this table. Pacemaker and pace model, it's used mostly for up to 5 elements, and but it can be very accurate. So GraceFS model or Grace 1-layer or 2-layer models, they can be, they have no limits. So it's mean in principle you can parameterize even the GraceFS model to the whole periodic table. Maybe accuracy would not be that nice, but still you can do it. We also try it, by the way. And now we can kind of parameterize these models to different favors of these models, like 1 layer, 2 layer with different cutoffs, maybe different hyperparameters and complexities towards larger data sets. So we can go to these foundational models. So we have pre-trained model for MP trajectory dataset. Mostly this is a collection of 1.5 million DFT calculation of approximately 150,000 material from materials project. It does contain the relaxation trajectory from WASP. And this is a publicly, so we didn't yet publish the paper. It's not yet the final model, but we make them publicly available now. So in order to deal with these foundational models, there is utility called Grace models. Of course, you can do it all from Python. It's not a problem because all these utilities is just wrapper around some Python function if you want to do it. Especially this Grace models is nothing more than just some manager over the files that you saved. So what I'm gonna do now, I would execute this Grace models list in order to show the available models. Yep, here we go, available models. Currently, we do have 3 models fitted on materials project. Grace 1 layer with cutoff 6 angstrom. We have some timestamp here, but it's not the latest one. We did not yet make them publicly available. And then 2 layer with radius cutoff 6 and 2 layer with cutoff 5 with slightly different architecture. So actually 3 models that we decided to put it on publicly available. So there's under academic software license, so you can use it for academic research. And I want to maybe demonstrate. Yep. So what does this model could be used for? So there is different way how you can compete and use these models. One of them is reflected in this MathBench Discovery leaderboard. You have a reference here, or just Google for MathBench Discovery Materials Project, which is a kind of test designed to simulate high throughput discovery of new stable inorganic crystals. So it means that, let's say this group of models shown here, this is a, Grace is not shown here because we didn't push it there yet. So this set of models, once they're trained on the materials project, mostly they're trained on materials project dataset, as we did. They could be used to relax not yet known materials configurations. So there is another dataset with 200,000, 250,000 DFT computed structure that came from Miguel Marquez, and it's a core of Alexandria database. And then you can kind of estimate how reliable model trained on materials project, different models, how good they do learn the chemistry and energy landscape in order to make prediction and relax on not never seen before chemistries and maybe find more stable compounds that is below the known convex hulls that came from materials project. And if you find these compounds, stable compounds with better or worse success rate, which is measured by precision or accuracy or other metrics, which could be now kind of formulated in average F1 score, which is average, geometric average of precision and accuracy for new stable materials discovery. So the larger the better, the closer to 1 the better. And it's kind of show how good your model in predicting this new low energy materials. And the second kind of type of competition he recently introduced is the thermal conductivity prediction using Pono 3 pi, so anharmonic contributions. It means that it does require quite accurate forces. So and so the smaller the better this kappa thermal conductivity accuracy, kappa SRME, the better. So we can now combine this F1 and kappa because it's just measuring 2 different aspects, and our Grace models look like that on this Pareto front. So ideal sweet spot in this corner, and of course this equiformers and non-rotation invariant models, they're quite good in predicting F1 score, but they're quite bad in predicting the forces, and vice versa. So our set of Grace models currently push forward this Pareto front in terms of F1 and this kappa. So we're gonna use 2 of these models now in our remaining 20 minutes to run some dynamic, because that's one of the foundational models that we make available. So you can see two-layer models which push this Pareto front further, and you can see this one-layer model which is quite close to another models that is around. But this is one layer. It's perfectly parallelizable over MPI, and then it has quite good performance as well. So not as bad as two-layer models, other two-layer models. Okay, so let's go to the tutorial page. So you can, once again, download all the models. Then it will be downloaded to your home folder.cache grace subfolder. And you can use them either in AC. So for example, I would demonstrate foundational models, Python AC using Grace FM. You can use them in AC, just creating calculator from that. It's nothing more than just, so all this foundational models is just TensorFlow saved model format, as we have seen before and generated before. They just have special location on your computer. Let me see. So I load, for example, this one layer model. You can provide it's either by name or by this, for code completion, you can use this Grace models class just for syntactic sugar. Let's say we take tungsten. Once again, we do have a JIT compilation over the first run, but then it's super fast. We can compute phonons. In that case, it will be yet another JIT compilation because it's 7 by 7 by 7 supercell for computing phonons, and we take maybe 5 to 10 seconds, as far as I remember. And you get this phonon curves. I have to admit that I do run it now on my local machine. We just have only RTX 3060. It's not A100, it's just typical gaming previous generation GPU, which is enough to run this type of models. Okay, so it should be as simple as that. So you just create calculator equal Grace FM and provide the name of the model. And it will be downloaded if it's not yet downloaded, otherwise it will be used from the cached location before. So now we can check how we will use it in LAMMPS. Let's use it in LAMMPS. But in principle, it's exactly the same approach. Now I will switch to GL Atom 2 because just to make it faster, but we go to this foundational model, LAMMPS. Let's say we have platinum surface. So here, the main point that we define pair style Grace path variables just for us to see when it does the padding, and we just provide the home folder path. I introduce it here with this special scripting language of LAMMPS. If you like it, if you don't like, just copy paste the absolute path here. You can always get it with Grace models list command. Just pass to this two-layer model with 6 cutoff, 6 angstrom cutoff to have platinum oxygen surface, where we will run some minimization and then short MZ for 1000 steps at 300K NVT ensemble. So let's see if it would work. I hope it would. So as you can see, it does load the model from this location, the same information about the padding, mapping of the elements, I mean 59 and 51 from the collection of the platinum and oxygen. And it happens several times, this padding, during the minimization, but after that it's quite fast. So it's running dynamic. I think I can even show you the 1 second. I can even show you the trajectory here. No, 1 second. So this is Avito, and in Avito I will load this foundational model, LAMMPS, platinum surface, this dump file. Yep, this is our platinum surface with oxygen atom. And if we do run minimization and dynamics, then you do see that it does dissociate on the surface. Sometimes you have to play maybe with initial condition as usual, so there is no guarantee that every model will do it, but this one did, and this is nice. This is expected behavior. Or you can make an ensemble of 3 foundational models and see when they always misbehave or when they have more or less reliable prediction. as an idea for some small study project. Okay, second example. That was it about this example. Second example is the simulation of ethanol and water. For that, I would use here. I would use one-layer model. Unfortunately, the currently publicly available models, they do not support the MPI parallelization because we introduced it slightly later. So we have to kind of resave them and re-export. But if you would parameterize your model using Grace one-layer preset, which could be quite accurate, you can parallelize it with MPI. I want to bring your attention here that I think an FAQ. Yeah. How to run Grace one-layer model. In principle, it's you do run MPI run with NP -4, let's say, and this is, to be honest, just answer from ChatGPT how to make MPI run works with different CUDA devices. That's what was working. I didn't test. Maybe it's a better way, but at least you can use it as a starting point for your code snippet. But let's go back to the foundational model. It's ethanol with water. So in that case, the only difference that it's just different path to the model, and I prepare already before the structure. So it's just 3 elements, CHO, and if we do run it once again, it should be running out of the box. Once again, sometimes you will see this recompilation, but they will be less and less frequent on the long run, unless you really have dramatic geometry change. And after that, so maybe it's too frequent output, but let me visualize the trajectory. So now with water dump. Yep. Yeah. This is stable dynamics, 300K, and it should condense in order to increase the density. I think I should wrap the atoms. That's the proper representation. Okay, is it finished? Okay, then at the end it's finished and it was stable dynamic. Oh no, it's still running. So I think you're already convinced that it's stable, and you can see that its density is increasing. So it's really try to do this trick when you mix ethanol and water to reduce the to increase the density and reduce the volume. Okay, so probably you will have a question if you want to fine-tune foundational models. That will be upcoming because we didn't release it yet, so it will be published at a later date. How to do it? For that, you will need not the models that you have already now, the exported saved model, because they have no the fitting utility. It's only the kind of so-called saved function for the prediction. For that, you will need the checkpoints, which we'll make available maybe later, but we plan to do it in the midterm or short term, hopefully after Christmas. I think that's it for now. So if you do have any questions, so probably we can stop recording if it was recorded. So if you do have any questions now, you can ask them without any hesitation to being recorded. Are we